Hi everyone. So in this lecture we're going to talk about running water, but really what we're talking about here is all water exposed at the surface or moving through the hydrological cycle. So that includes oceans, but a majority of this lecture is going to cover rivers, streams, lakes, things of that nature. So generally water that moves across the surface of the continents. And so some common sort of water facts here. So it's the only common substance that can be solid, liquid, and gas within the ranges of temperatures and pressures found on the Earth's surface. And this is the part of the Earth systems that we refer to as the hydrosphere. So that's the part of the geosphere that contains all water at or near the Earth's surface. So here's a little breakdown of the percentage of surface water on the planet up here in the top left pie chart here. 97.2 of all surface water is held in the Earth's oceans, with the other 2.8% making up most of the water that we see either held up in glaciers or in groundwater and these sorts of things. We have a whole section on groundwater, so I'll skip that for now, but that's about 0.62% of the hydrosphere. By far, the most of that 2.8% up here is made up of glaciers. So most fresh surface water is held up in glaciers, and then about 0.5% in groundwater. And then this little sliver over here is all of the freshwater lakes, saline or salty lakes, soil moisture, stream channels, etc. And you'll notice freshwater lakes make up only 0.009% of the water available in the hydrosphere. And then you can see as it moves down about 0.001 at the low end, or no, I guess stream channels are at the low end at 0.0001. And then the atmosphere, inland seas, and soil moisture make up the rest. Okay, so less than 1% of the Earth's water is readily available to humans as fresh ground or surface water. And again, that's because most of the fresh water on the planet is being sequestered in glaciers. To put it another way, you can see here kind of I like this figure because it shows, again, that same breakdown of ocean versus freshwater, and then it takes that sliver of freshwater and it shows you that it's glaciers and groundwater, and then there's surface water, and it takes that little sliver and blows that up, and you see that it's mostly snow and ice, and then lakes, soil moisture, and then swamps, rivers, and also this thing here, which I think is interesting, is biological water. So that's the water being stored in biological organisms at the surface. So water that's in your bodies, water that is that trees are using to photosynthesize, etc. So this is another way to look at it. And this figure, it just kind of blows my mind. So if you take the surface of the Earth, you take the whole globe. If you were to take all of the water by volume on the planet, it would make up this little kind of marble compared to the size of the Earth. So all fresh water, all water, period, even in the oceans, would all make up this section here. All fresh water make up this medium-sized circle or sphere rather here, and then this tiny, tiny, tiny little dot here, that's all fresh surface water. Okay, so pretty astounding. Most people don't believe this when they see it, but that's all the water on the planet. So we'll talk about the hydrological cycle. So water is a renewable resource unless we consume it faster than it's able to be renewed. And it gets renewed through the hydrological cycle. And that involves evaporation into and precipitation out of the atmosphere. So the atmosphere is sort of the great filter because it only dissolves, or it only evaporates rather, the water portion of any surface water or ocean water that is evaporating, leaving behind most of the contaminants and solids and things like that as they don't evaporate. And so then that rains back down onto the earth as relatively filtered, clean water. And precipitation onto land, that precipitation will then re-evaporate. Some of it will infiltrate into the ground, and then some of it will run off over the ground surface. This is what that hydrological cycle kind of looks like. This is out of your textbook. And so this is, I think, annually. Basically, you get evaporation, mostly from the oceans. And I want you to think about why that might be. It's been then caught up in the atmosphere, in clouds and other vapor bodies. A large portion of that will precipitate right back into the ocean. The rest will precipitate directly onto land, where it will either re-evaporate, or something we call transpiration is when you get evaporation on land. Some will infiltrate down into the ground, and that becomes part of the groundwater, and then eventually that groundwater, when an area is low enough that it reaches the water table, that's when we see streams and lakes. And the rest just flows down the land as runoff. And it will seek preferentially the lowest point, which is the ocean again. So eventually all water kind of makes its way to the ocean, unless it's being dammed up or used in some other way, or it's trapped by mountains or something like that. So the oceans are the largest source of evaporated water, and that's because of surface area. In order for things to evaporate, when water evaporates, it's the uppermost layer of any water body that's evaporating because it's in contact with the atmosphere. And the ocean simply has a lot more surface area and contact with the atmosphere across the whole globe. So it is by far the largest source of evaporated water. And for the water cycle, basically, about 100 million billion gallons, or 380,000 cubic kilometers of water move through the hydrological cycle per year. So that number doesn't change very much at all. So in terms of population, it's important to think about this, because the hydrological cycle again is filtering out water and keeping it a renewable resource. But as population increases, so does consumption. So the more we consume, the less likely it is for the hydrological cycle to keep up and replenish that fresh, clean water. So for surface runoff, I'm including stream flow in this because that's what most runoff does, right? It's water that's running across the surface. And this is rain that does not infiltrate the ground as groundwater, nor does it evaporate, nor does it get sequestered up into plants. And the amount of surface runoff is dependent on the infiltration capacity of the surface where the precipitation is landing. And that's controlled by the intensity and duration of rainfall. So if you get an increase in rainfall, it would make sense you get an increase in runoff. And anybody who's been in a storm, if it's just a light drizzle, you can imagine how the roads and the gutters and the streams look. And if you're in a big torrential downpour that lasts a day, we get flooding, we get flooded streets, your yard could get real puddly and things like that. So the intensity and duration. Then there's the saturation of the soil. So is the soil already saturated with water? Obviously, you can't keep filling up an area that's already filled with water. So that makes a big difference. Soil texture. So this is the size and the shape of the soil grains. If you have small rounded grains, you're going to get less infiltration than if you had, let's say, gravel or something like that, where you have irregular shapes, so there's more pore space between the grains, and so more water is allowed to sink down through. So for runoff, again, if you have real muddy soils or just real fine particles, you'll get runoff that way. The slope of the land, so an increase in slope is an increase in runoff. So if you have a real gradually sloping landform, like a real shallowly sloping hill, you'll get more infiltration because the water has time to move down into the soil as opposed to just running straight down a really steep incline. And then vegetation cover. So if you have an increase in vegetation cover, you get a decrease in runoff. And this is because that water, when it hits, it's going to be taken up by vegetation and not allowed to run down slope. So for streams and river systems, a stream and river system is any body of flowing water confined within a channel, regardless of size, right? So the thing I like to say is all rivers are streams, not all streams are rivers, okay? So the technical term for all of that, whether it's a creek or a stream or a river or whatever you want to call it, in geologic terms, we kind of call this all streams, like it's all water streaming across the surface. It's responsible for the erosion and transport and deposit of geological materials on the surface, and therefore it shapes the landscape by depositing and carving, and it modifies the landscape by eroding existing structures, mountains, hills, etc. And so here's a river channel here, and it's one thing I want to point out is that the velocity here in the middle and at the top is the fastest. And this is due to the fact that the closer water is to any kind of surface area, any kind of contact with the stream channel, it's going to experience some amount of friction. And so you have maximum friction around the stream channel, and then as you move in one, you've got this in contact with water that's at the highest friction. So it's a little bit faster, but not much. And then it gets a little faster and a little faster and a little faster till we get to the middle, and that's where the water is going to be the fastest. It's the furthest away, and it's only in contact with other water that's getting gradually less affected by friction. So for erosion and transport, erosion is the ability of a stream to erode and transport material, and that's dependent on the velocity of the stream, which is influenced by the following three things. You have the gradient. So gradient is the change in topography over some distance, across the landscape. So if you're going from a real high to a real low, as far as topography goes, over a short distance, you'll get steeper slopes and thus faster streaming, as opposed to low slopes or a low gradient, you'll get slower moving streams. Also, there's the size, shape, and roughness of the channel. And this harkens back to the last slide where I was talking about the friction along a channel. So that area where the water is in contact with the stream channel, we call that the wetted perimeter. And that is, again, affected by frictional drag. And then you have the discharge, right? So that's how much water is moving through the square area of the stream in cross section, and I'll show you what I'm talking about there. For gradient, whenever you're feeding a stream, we call that the head. So that's the head. Usually that's at a higher topography, in this case mountains. So it's going to be faster here, right? It's going to move through these areas up here much faster, cutting a certain kind of erosional feature. And then as the gradient gets more gentle, then we start to see a different behavior in the rivers. Up here we have rivers that we call braided streams. And down here we have rivers that we call meandering rivers. And then where that river runs into the base level water body, in this case the ocean, we call that the mouth. So I know when I took this class, I thought mouth meant the head of a river, like the top, but no, that's the head. And then the mouth is kind of the end of the river, if you want to think about it like that. And here we're going to talk about this in topography, if we haven't already, and that is that here you'll notice there's an area here where the grade is much steeper over just this small area, whereas here it might take that same amount of slope and stretch it out over this whole area. So this is the difference in gradient that I was talking about. So when we're talking about the discharge of a stream, we're talking about the amount of water that flows past a certain point in the stream in a given unit of time. And that point is, you can imagine you're standing on the side of the stream and you're looking across the entire stream. That's the point, across that section, just at that one point that you're standing in. And so we call that discharge, and we use the variable Q to denote that. And so you have the speed right here, and then it's moving faster here, and then it's moving faster here, right? But what we do is we just take that speed, we measure it here, we measure it here, 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 and here. They're going to be different. But we can average those up, and then we can multiply them by the cross-sectional area, which we use the variable A for. And so if this is 1 meter here, another meter, and then it's a meter deep, in 2 dimensions, this is 1 square meter. And so the distance across this entire stream is 10 square meters, just at that one 2-dimensional area. And we multiply that again by the speed or velocity of the water as an average, which we denote with the variable V. And when you do that, if you have meters per second as speed times 10 square meters, you get the units that denote discharge, and that's equal to the volume per unit time. And if we're multiplying meters squared by meters per second, we get meters cubed per second. And that is the units for Q, or discharge. So let's move now to some of the features that we see as far as stream systems are concerned. And I want to talk about drainage basins. So a drainage basin is an area from which the stream draws water. And the size of the stream is dependent on the area of the drainage basin, as well as the climate, vegetation, and underlying geology. And this makes sense. Climate will cause more or less water to be available based on temperature, right? If it's colder, there'll be more water available as long as it's not frozen. And if it's warm, a lot of that water will evaporate before it makes it to the stream. Same with vegetation. A lot of times vegetation will sequester water more readily and not allow it to move down into the stream channel. And then the underlying geology, if we have mostly muddy soils up here in, let's say, a mountainous region, you're going to get a lot more runoff down into the stream. Whereas if you have a real gravelly area, you're not going to get as much water because most of that's going to sink down into the ground as groundwater. And it might eventually make its way to the stream. In fact, it most likely will, but it takes much longer to get there. And so these streams tend not to be as fast and have as high of a discharge. And here we can see a drainage basin cartoon sort of up here. And you'll notice this pink part here is bounded on either side by a ridge over here and a ridge over here. And so water that falls to the, let's say, to the left of that ridge is going to fall into the pink area. And similarly to the right of this ridge, fall down into that pink area. Whereas water on the right side of this central ridge and on the left side of this far ridge down here, all that water is going to run down into this stream basin. And so this drainage basin and this drainage basin are different drainage basins, even though it's likely eventually they're going to meet up. So if you think about it, we can have really, really small drainage basins locally that feed into much larger drainage basins. And that looks something like this. So here on the left, we see the Yellowstone River basin being fed by the highlands in Yellowstone National Park. Here's Yellowstone Lake. So all the rainfall, snow melt, everything, it's running down through these various rivers here, the Yellowstone River and the Bighorn River, moving through Billings around Cody there, and it's moving east through Wyoming. Then there's the Bighorn Mountains and any kind of rainfall there. The head of the two new rivers begins, that's the Tongue River and the Powder River. And then just past Miles City, just east, everything converges into the Yellowstone River. So this is the Yellowstone River drainage basin. And that just makes up this little portion here of the Missouri Basin. And that's all the rivers and basins and everything that are on smaller scales, of which Yellowstone is one, running into the Missouri River. The Missouri River then meets up with the upper Mississippi and eventually the Ohio, the Arkansas, Tennessee, and lower Mississippi. These are each individual drainage basins that we've categorized. And that makes the overall Mississippi River drainage basin, which covers, 2/3 of the United States almost, all draining down eventually into one main section of the Mississippi River. So in this way, I hope you can see how, one large drainage basin is made up of smaller drainage basins, which are in turn each made up by smaller drainage basins. And if we wanted to zoom in here, we'd probably see that the Yellowstone River up in this portion here probably has a number of smaller drainage basins, and this could go on for a long time. I mean, almost to the point where you could just look at a little divot on the side of a creek where a little stream is running into the creek, and that's also a drainage basin. So let's talk about some of the work that streams do. Again, I said erosion, transport, and deposition. And as we talked about in sedimentary rocks, erosion is the removal of rock and soil that's been weathered in the case of rock, or soil that's been deposited in the case of other soily sediments. And streams erode their beds by abrasion, sandblasting, and picking up loose debris. And here's a nice eroded surface next to a creek here. I believe this is somewhere in Maryland, I guess. But you can see here that the river is cutting down through this sandy sediment area. And where is that stuff going? Well, on its way through the drainage basins and through stream channels, it's trying to reach what we call base level. So the base level is the lowest level to which a stream can erode. And it's usually a larger body of water. So we don't really think of, if you have a smaller river running into a bigger river, we don't really think of that river, the bigger river, as the base level. It's the base level of that smaller stream, but true base level is usually where streams are running into standing bodies of water, such as oceans, lakes, other streams, like I said, but usually oceans and lakes. And here we've got resistant beds, different sedimentary layers here. And so you can have smaller base levels, right? But then you have this larger base level with this feature down here at the mouth that we'll talk about. One thing about base level that I want to talk about is left just to nature, you're going to have drainage basins running into a central river or stream that eventually finds its way to the sea. And that's all fine and good. And we can imagine it, it's eroding these things at fairly regular rates up here where it's moving through higher topography and eroding. It's also eroding materials down here, but mostly it's depositing materials down here. And I'll talk about that. But if we were to go and put a dam in here, right across this way, now everything's running down into here. You'll notice a reservoir has formed. And so now the new base level is here. And whereas up here, the profile of the stream is adjusted to base level, up here it has to readjust itself to a new base level. And so whereas we were getting most of our eroded sediments from up here depositing down into this plain area here through the meandering streams and eventually running down into the sea, Now it's depositing all that stuff up here. And so here's the original base level. And now we have this new base level here, okay? And that's going to cause a lot more deposition up here and maybe less erosion here because the water is no longer rushing through this little canyon here. Now that canyon has become a lake, basically, or part of this larger reservoir. So on its way to its base level, any stream or river is going to pick up sediment. And as it's moving through the landscape and picking up this sediment, it's transporting it in two different ways. The first way is what we call bed load. And bed load is the heavier material that's moving, but because of gravity, it's not being picked up and being carried in the main portion of the water column, but rather it's sliding, rolling, or bouncing along the bottom. So it's being pushed, but it's along the bottom of the stream. And when it's bouncing, we call that saltation. We have fancy geologic words for most of these. Sliding and then rolling. So this is bed load here, okay, in the lower portion. Then you have suspended load, which is the lighter material that gets carried higher up in the water column because it's much lighter and much smaller. And so it doesn't sink to the bottom. The water is moving fast enough that that load is being suspended. And that falls into mostly the clays and the silts in the suspended load. But you can also have dissolved load, which is invisible to us. But that you can imagine like a river that's got some salts dissolved in it. It might not taste salty, but there's definitely salts being eroded somewhere and dissolving in that river. So that we call dissolved load. And it's a form of suspended load, but because it's dissolved, we don't really consider it sediment per se. So if you get something called turbulent flow, which is when the flow is moving in such a way it can dislodge sediment and keep it suspended. So we see that here with this bed load here. You can get turbulent flows where you actually start to get the water moving just like turbulence on a plane. It's moving sort of up and down in this direction. It can carry sediment up and begin to suspend it. Streams with smooth laminar flow tends to be the type that deposits material, right? So in a real turbulent river, you're mostly pushing sediment. And then as streams begin to slow down into laminar flows, which are just smooth streamlines, that's where it's dropping most of its load that it picked up in its turbulent flow. And the only thing you have left then is just particles, smaller particles of silt and clay. So some vocab words there to make note of. And so for transportation, we have a couple things that we talk about. The first is the capacity. And that's the maximum load of solid particles that a stream can transport. And the key here is higher discharge rivers, higher capacity. Okay. And then there's competence. So that's the maximum particle size that can be transported. So rivers have sort of a natural speed at which they move. And based on that speed and the types of sediments that are around, it can only transport certain particles. After a certain point, that stuff gets to be too big, and that river's not going to move that stuff. That's why you see rocks in rivers, right? It's not going to move this boulder anywhere, but it can move all the mud that you see that makes this river brown, okay? And one thing I want to point out is that the greatest erosion and transport of sediment occurs during flooding, because that's when any kind of stream that floods up along its banks is going to begin to pick up smaller things that it's competent enough to pick up and bring that back down into the stream channel, okay? So when we have flooding of rivers, whether they're fast-moving rivers or, they're going to increase their capacity and competence in some cases. So let's observe and interpret this graph of a stream velocity versus the mode of transport for different sizes of sediment. So at high velocities, sand and smaller particles are carried in suspension. And so you see here that at, this is velocity from low to high here in centimeters per second. And at high velocities, you get sand and smaller particles being transported as suspended sediment here, right? You also get moderate velocities where you can get silts and clays suspended, but sand moves as bed load at this point. So this middle section is showing you, that you get fine sand, and gravel as bed load here, right? Whereas up here, you get that stuff as suspended sediment up to a point. But then we get down to the lowest velocities, and clay and silt can remain as bed load here, but most everything is going to be deposited at this point. So at really low velocities, silt and clay might still be suspended sediment, but you'll get deposition of just about everything else, fine sands, and gravels. So as we reach those lower velocities where competence is reduced, sediment again begins to drop out of suspension, especially the largest particles first. And they begin to deposit material, either along a floodplain or a kind of like a real gradual shoreline until they reach their base level. And at base level, the velocity of that river drops to 0, okay? So at that point, that river is no longer able to push sediment because that river has now run into a larger body of still water. And so all of the sediment that river had been carrying gets deposited. And this deposition makes what we call a delta fan or an alluvial fan. And it creates basically a wedge-shaped fan of debris. Here's southern Louisiana here. Famous, this is the Mississippi Delta, for those of you that like the blues, or have been to New Orleans. And this is showing you that the Mississippi River at one time ran over here and was depositing a deltaic fan here. But over time, meandering rivers change direction. And so at time 2, it was depositing a delta here. Then at time 3, here. Then at time 4, this big delta out here, some of which is still exposed here around New Orleans. Then you have time 5, where it was depositing a fan here. At time 6, where it was depositing this fan here, that material is still present. And then 7, it's creating a new fan. So this is where the new fan is being deposited. And we can see that as basically, I don't have a picture for time 1, but you can see time 2, this is what the shoreline looked like. At time 4, this is what the shoreline looked like. And at time 5, this is what the shoreline. So it's slowly depositing material and it's building up these delta fans, or deltaic fans as they're called. And New Orleans is built right smack dab on the top of this huge delta complex. And prior to the stream or river reaching the mouth and forming these deltas, it's also depositing sediment in the flatter plains leading up to that. And that looks something like this, and we're very familiar with what this looks like here in the Grand Rapids area. If you think about it, you could put Grand Rapids somewhere over here, let's say, and you can see valley walls on either side. The school is built kind of on the beginning of one, the big hill up where you get up into Heritage Hill. And then over here on the other side, you could imagine this is kind of like where John Ball Zoo is and some of those areas to the west. And as rivers move through these big kind of floodplain areas here, we call these meandering rivers because they kind of just meander around. They're moving really slow. And they erode and deposit based on this movement here. okay? So the whole area between the two valleys, or between the two valley walls rather, we call the floodplain. And there's a number of different terms that we use. So this is the main meandering river here. And you can get back swamps, which we have around the GR area. If you go over by Millennium Park and a few places. Oh, I guess a good one would be Riverside Park. There's like kind of those swampy areas over by Riverside Park as well. And then we have little things we call Yazoo tributaries. And this is where back swamps have little tributaries that are running down and eventually will kind of come into contact with the river again, possibly, or else that water will just eventually seep down into the ground as groundwater. And so these smaller little tributaries from these back swamps, they're picking up sediment and depositing sediment as well. And that's where we see a lot more fine sediments, whereas the main meandering river is depositing more coarse sediments. And when that all floods, the water will fill that floodplain, hence the name floodplain. And when it does, it overflows its banks and floods, and it deposits sediment just along the side. And this is what we call a natural levee, where most of the sediment that comes up out of the river immediately as it's flooding gets deposited right on the sides. And then as it moves out, it's depositing finer and finer sediments as it's moving away from the main stream channel. So that looks something like this. And then if we're at higher topographies, where rivers are moving faster through generally more kind of rocky areas, we get these narrow V-shaped valleys, right, where the river's kind of moving more in a straight line. It doesn't meander as much. It finds a weakness in the rock as it's moving and it's eroding it, and then it's just slowly eroding down, 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 down. Kind of like what we looked at in the mass wasting lecture with the Grand Canyon. That river is just cutting straight through that canyon. Once it creates the V-shaped valley, or starts to, it just continues to move through that channel. It doesn't really have a chance to move around. It's going to naturally exploit that channel and just make that channel bigger and bigger and bigger and bigger. Okay. Then as we get closer to base level, we'll get a meandering river beginning to form. And you might still be in a rocky environment close to base level. Think California. There you're going to see that meandering river literally cutting into the sides of a cliff face, sort of in this kind of environment, but closer to base level. So the river's moving slower and it floods more often. And as it floods more often, you're still getting erosion through this cut bank here, but you're starting to develop a floodplain because that river is able to flood closer to base level. You get floods at base level, closer to base level. And so that's a depositional feature where now it's meandering through and it's depositing, and then it's cutting through and meandering through the stuff it's already deposited and then depositing more material. Eventually, as we get the closest to base level, the primary process here is now mostly just deposition, right? So think here, the primary process here in a V-shaped valley is erosion. It's just eroding. Here it's eroding and depositing, and then here it's mostly depositing. And this is kind of the area in West Michigan that we live in, all right? So there are spaces higher up where the Grand River might have some kind of narrower V-shaped valleys being carved, but most of the head of the Grand River as it moves through the eastern part of the state mostly looks like this. And then once you get down to like Allendale, Nunica, places like that, we're mostly just in these well-developed floodplains. Where I live in Allendale, it looks a lot like this. So let's talk about stream valleys and floodplains. So the combined effects of erosion on the cut bank here and the deposition at the point bar here and the downstream meander produce this broad, flat expanse of land covered with sediment, and that's what the floodplain is. Now, before I took this geology class, I thought that the glaciers melted and at one time the Grand River Valley here in town was just all one giant river, right? And then as the water source dropped down, then you started to get rivers that are just kind of left over from a much larger river. But that is absolutely incorrect. It's a nice uninformed idea, but if you were to dig down into the sediment, you would see evidence for previous stream channels. And really what's happened is the river's always basically been about the same size, but it's just meandering back and forth through this over thousands and thousands of years. So right now, this river in this example, it's moving along, and on the outer portion of a curve, that's where the most erosion is happening, because that's where the river is the fastest. It has the most velocity as it's coming around this corner. Its velocity is on the outside. And if you've ever been on a merry-go-round, you know the further you move out from the center of a merry-go-round, the more velocity you're feeling on your body physically. If you stand in the middle of a merry-go-round, you don't feel it hardly at all. What that's doing is it's cutting into the side of this valley wall here. And as it's doing that, at this lower area of velocity around the corner, it's depositing material. And if you've ever been canoeing or kayaking or even just walked down to a river and looked at it, you'll see this here, we call this a point bar, okay? And it's usually an area when you're coming around a corner on a river, you'll see there's a sandy area on the inside of the curve, and then the outside of the curve is usually cutting into a, like in our case, like a sand dune or cutting into, you know, basically the like a big hill. And there would be, you know, trees and forest up here, but down in the plain of the river, it's just cutting in. And then it goes through this other curve, and now it's eroding this area, and it's depositing sediment here, and so on and so forth. And this blue line again represents the maximum velocity. And you can imagine it's going to keep cutting over here and depositing here and cutting here and depositing here. So eventually this river is going to hit here, and then it might come over, go all the way over here and start cutting this guy, right? And then moving back down over to here. So this is how they basically meander, is they're eroding on the side, depositing on the inside, right? And so that's how the river over time moves about. So some features that you can get, here's the Green River in Wyoming. And you'll notice this river is meandering along, and you can see the main channel here, right, going down through there. But you've got this big section here that's really not part of the river so much anymore. It's kind of still attached here at the bottom. You've got this little guy over here feeding into it. But what will happen is you'll get meanders that are eroding and eroding and eroding, and eventually this inside here and this part here will begin to erode so close to each other that they'll form a neck, okay, between the two meanders. And as those necks get closer and closer, or as that neck shrinks, I should say, as those meanders get closer and closer together, eventually the water will just cut through that and create a cutoff. And now the river just flows through here, leaving behind this big horseshoe shape that we call an oxbow lake. And you can see these all over Michigan. The Grand River has a number of them. The Kalamazoo River in Saugatuck has an oxbow lake that's famous enough that they built an art school on it and call it, you guessed it, Oxbow Art School. And this is a real common feature, and it has to do with just the way that these meanders erode towards one another over time. I encourage you to watch this video. It probably does a better job of illustrating what I'm talking about here. And we're going to skip this activity for this particular class, so don't worry about that. But I do want to include this slide because I want you to see this river in action. So let's move on to flooding. So flooding is the #1 natural disaster in terms of loss of life on the planet. It's a natural phenomena and it's beneficial. Flooding has always occurred as long as there's been surface water and rivers, and it naturally deposits nutrients, replenishes soil moisture. It's part of the natural process, and it carves the land and it feeds certain types of life and feeds the nutrients found in soils. But as population growth increases and urbanization increases, as has been a theme in this class, natural processes then become hazards or risks, okay? As we move into areas, the natural processes of those areas affect our populations, okay? And that can mean loss of property, damage to property, and loss of life. So, flooding can occur during heavy rainfall or snowmelt when the ground is already saturated, as is the case here very often in Grand Rapids. It can also happen when rainfall exceeds the amount of rain or amount of water, I should say, that the soil can accommodate. So it's not sinking down or infiltrating anymore. It's exceeded infiltration. The soil is completely saturated. And so all of that water upstream or in the drainage basin is just going straight down into the stream system as runoff. And the severity of the flood is really the volume of and rate that water enters the stream, okay? Streams can naturally sort of move water along, and they do it all the time. The river might be higher or lower, but it's not exceeding its banks, so it's not flooding. But if you get a larger volume of water that's moving really fast, you're going to get flooding. So for infiltration capacity and runoff, the way that infiltration capacity controls surface runoff is the, again, intensity and duration of rainfall, the saturation of the soil, the slope, and the vegetation cover, which I talked about in an earlier slide. The faster the surface runoff, the higher the probability of severe floods. And here's a flood that's just moved through and completely destroyed someone's driveway. So this was a lot of really fast moving water came through and really just ripped this whole area apart. All that sediment fell down into this river is now being carried away, including some parts of people's driveways and maybe even a bike or two. So as far as flood characteristics for upland floods, we tend to call these flash floods. They're really powerful. They happen with little to no warning. And they're, like I said, usually in areas of moderate to high relief. And the area of impact is really just in those kind of V-shaped valleys. And it happens very quickly, and it does a ton of damage in a really, really short amount of time, as you can see here in this picture. And then for lowland floods, they're typically longer in duration, and they affect a much larger area. They have a larger drainage basin, so the larger volume of water is involved, because this usually these lowland floods, or these lowland river systems, I should say, before they're flooded, they're getting water from every drainage basin upstream from them. So they tend to be larger in volume, and so when they flood a lot more. And they're usually because of prolonged rainfall or some extensive amount of snow melt very quickly. And this is here in downtown GR. This is a flood from, was it 2013? I remember this well. In fact, I know somebody that works down in these offices here, and they snapped a picture, and there's literally, half their window to 3/4 of their windows were underwater. So it's kind of like looking in a fish tank. And they've built these buildings to withstand this, but there were many parts of downtown GR where they had to put sandbags up, or this could have been a lot worse. So as humans are apt to do, we tend to really alter the landscape, and we try to control what rivers do, especially as they're moving through an urban area. And some of the modifications that we put in place alter the timing and the amount of runoff running into a stream channel at any given time. And oftentimes when there's large amounts of rainfall, that just changes the way that things flood. Generally, we're talking about bigger floods occurring, right? And when that happens, the flooding will extend beyond the sort of historic natural floodplains that were in place before urbanization. And it will cause the floodplains to be much larger, encroaching into those urbanized areas, into neighborhoods and things like that, that maybe were once protected from flooding when there wasn't as much modification happening upstream, and I'll talk about that. So you can see here, this is kind of a cartoonish drawing, but I want to kind of show you that generally a river before urbanization, you have what we call a flood stage, and that's the highest stage that the river will flood, sort of at its maximum flood event. And you see here we have this kind of nice normal curve here. But then after urbanization, you get discharge to the point downstream from modifications, which I'll talk about, that will exceed the flood stage, and that's when we get flooding, right? After urbanization occurs. And this graph on the x-axis here is time. So really what we're seeing here is over time, the river might not even reach that flood stage, whereas here it exceeds the flood stage for a short period of time, very suddenly and very, sort of powerfully, because of the amount of discharge moving through the area per that unit of time. So in order to help control or mitigate floods and try to reduce their damage, we employ a number of different techniques. The first is we'll put dams in to control the volume or rate of water moving through a river system. We'll put retaining basins in to control the volume and rate. Sometimes we'll put flood walls in as a barrier between the river and the surrounding floodplain. As just flood walls, actual walls, we have a few here in GR, especially over on Market, the Market area there. And then we can also put in artificial levees. So remember I talked about there's natural levees when rivers flood. They create kind of a little mound on either side, running along the side of a river, and that's a levee. We can restrict floodplain development. That's the best solution. Just don't build where the water floods. But there's two main problems with mitigation with our first four methods there, as far as dams, basins, etc. For one, there's just increased complacency. So we build in high-risk areas because we think, well, the city's got it under control, no big deal, let's go ahead and build. It's also self-perpetuating. Areas downstream from barriers like levees experience greater flooding. So imagine this, you as a municipality, like a town, you build levees or flood walls, and great, your town never floods. But all that water moving through that stream that didn't make it over that levee or that barrier is now moving downstream to the next town, okay? And that might flood them, or if they have things in place, like levees and flood walls, now 2 towns worth of flood water is moving down to the 3rd town, and so on. And so they self-perpetuate floods. They just basically pass the buck downstream. So more levees equals more water surface above the surrounding floodplains, even at non-flood volumes. So what does that mean? Well, an artificial levee is a river channel that can hold more water, right? So we can imagine as you build a levee up this high, you can put more and more water into this river system, and it's not going to flood over onto these train tracks, right? And so the water then just moves downstream instead of flooding into an adjacent floodplain. And then the downstream communities experience greater flooding, as I said. So then the downstream communities then build more levees, and so on. Another thing that happens that's a real problem here is that by building a levee, you've allowed the water to move on past your town, well, eventually it gets all the way down to a city like New Orleans, which has levees, right, to prevent flooding. But all the towns upstream that have built levees, all that water is being pushed down. So New Orleans has had to build really large levees to make sure that the river is isolated from the urban area, namely New Orleans, that it's moving through. But then you get something like Katrina, and the levees get overrun, and then there's flooding in the city. Where's that water going to drain out of? Once it's flooded into these neighborhoods, where does that water go? Nowhere. You've built levees so high that that water can't drain back into the river system as the water level of the river drops back down. That also means that levees can trap the sediment that was in that water that flooded over. And that means that levees need to be constantly modified to hold back rising water, and that the water surface can be above the surrounding floodplain even at non-flood volumes. So you can get a river that's high enough within its levee system where it's above the height of your house if you're on the other side of the levee in some neighborhood on the floodplain. And so at any given time, if any part of that levee fails, all of a sudden all that water is going to flow out into the urban area. And so flooding is a real problem, obviously, and the ways that I think this is what I want you to take away from this is that the ways that we try to control flooding oftentimes just creates more problems for more populations downstream. Okay. And this is also true of pumping water too. This is a big deal out in Colorado and the southwestern states right now as well, where everyone shares the Colorado River. People are pumping from water upstream, and that's leaving less water for people downstream, et cetera. So it's kind of the reverse of what I just talked about. But you got to remember that as we modify river systems, it always has all these unintended consequences that we don't necessarily anticipate. And then we're just continuing to put Band-Aids and Band-Aids and Band-Aids and Band-Aids, and those Band-Aids are causing even more problems. So that's all I've got for surface water. Let me know if you have any questions. There will not be an activity in this coming lab for this, but I want you to go through this and use it to answer the discussion prompt that I put in. And I hope you found this interesting. And if you'd like to know more or want some additional information, if you're really into rivers and surface water and stuff, just let me know and I'll find you some stuff to look at. So I'll see you all in the next lab and have a great day.